The solution of some matrix equations can show a very useful phenomenon, which is that they may have eigenvectors and eigenvalues. The essence of an eigenvector is that when we multiply this eigenvector by our matrix, we're going to get back the same vector, possibly multiplied by a number, and that number is called the eigenvalue. If we think by analogy with ordinary geometrical vectors, when a matrix multiplies one of its own eigenvectors, the result is a vector that we can think of as pointing in the same direction, but with a length multiplied by the eigenvalue. The word eigen comes from German, where loosely speaking it means own or self. In fact, it is etymologically related to the English word own, eigen and own. For an eigenvector of a given matrix, when we multiply it by that matrix, we get back the selfsame vector, though possibly of a different length. So this is where the idea of self comes in with eigenvectors. The behavior of eigenvectors and eigenvalues of matrices is found in a generalized form in quantum mechanics, where we may have eigenfunctions instead of eigenvectors, though in a deeper sense, the ideas of what we call eigenfunctions and what we call eigenvectors are really the same thing. And we will in the end be able to use the matrix vector form even when we are dealing with eigenfunctions instead of what we might think of as eigenvectors. Hence, the essence of the ideas of eigenvectors and eigenvalues with matrices is particularly important in the mathematics we need for quantum mechanics.
So let's look at a matrix eigenequation. An equation of this form, a matrix A times a vector D equal to a number lambda times the same vector for a square matrix, is called an eigenequation. So this lambda is called the eigenvalue. This D is called an eigenvector. And if there are solutions of this equation, and that's not necessarily the case, they may only exist for specific values of lambda. So if this equation has a solution, which it might not, if there are solutions, they may exist only for specific values of lambda, for specific eigenvalues. So let's look explicitly at how we're going to solve an eigenequation for matrices. So we start out with our eigenequation, and then we rewrite it rather trivially by putting in the identity operator here. We can always do that because the identity operator does nothing. I times d, this vector, is just d. So we can always put an I in there if we want to. And so we can rewrite this equation. We can take this lambda I over to the left. So we've got this now just a matrix A minus lambda I times D is equal to 0. So all we're doing here is rewriting our matrix. We have to be a little careful with our notation here. This 0 here is not the number 0. It's actually a vector with elements that are all 0. And this notation is somewhat loose. We should have been clearer that this is actually a vector with elements 0 and not just a number. But once we've sorted that out, we realize that what we've done is we've rewritten this equation up here in this form. It's exactly the same equation, but now it's got a different character to it. It's saying some matrix B multiplying this vector is going to give us a 0 vector as a result. Now, why did we do that? Well, we know something about this. If some matrix B times a vector is to give us a 0 vector as a result, and the vector D itself is not going to be a 0 vector, that would be trivial, that means this matrix B cannot have an inverse. If it did have an inverse, which we could write as b to the minus 1, then we could multiply both sides of this equation here. B to the minus 1 times b is, of course, just I, on the presumption that this inverse exists. So that means b to the minus 1 times b times the vector d is just d. And that must be, of course, looking at the other side of the equation, b to the minus 1 operating on this 0 vector, a vector with elements all 0 in it. But any finite matrix multiplying a 0 vector must give a 0 vector. So there is no non-zero solution D. There's no vector D that isn't already just all zeros that can solve this equation here if this matrix B has an inverse. So by what we call reductio ad absurdum, B has no inverse. If it did have an inverse, we get to a silly situation here which can't exist, so therefore B cannot have an inverse. That's a reductio ad absurdum proof. So if we have this equation here, which was just a rewrite of our original eigenequation, for this equation to have any solutions, it must be the case that the matrix B has no inverse. Now, if the matrix B, which remember is just our original matrix minus the eigenvalue times the identity matrix, if that matrix B has no inverse, it means from the properties of our determinant that the determinant of that matrix has to be 0. Remember we said that before. If the determinant of a matrix is 0, the matrix is no inverse, and if the matrix is no inverse, the determinant is 0. That's one of the magic properties of determinants. This equation here will allow us to construct what is sometimes called a secular equation, and the solutions of that secular equation will give us the values lambda for which our eigenequation is going to have a solution. And once we've figured out those eigenvalues lambda, the values of lambda for which our eigenequation has a solution, it's relatively straightforward to deduce what these eigenvectors are. So, suppose we want to find the eigenvalues and eigenvectors, if they exist, of a 2 by 2 matrix like this. It's a square matrix. It happens to be a complex one, imaginary elements on the off-diagonal. So we write the determinant condition for finding eigenvalues. The determinant of this matrix has to be 0. That means the determinant of all of this matrix added up in here has to be 0. Now, the determinant of all of this stuff here, we can add everything together. We take our lambda and actually multiply the identity matrix by it. So that's this matrix lambda, lambda here. We then add these two matrices with the minus sign in here, and we get this matrix. So our equation now is we want the determinant of all of this matrix to equal 0. So our secular equation becomes the determinant equals 0 here, gives us all of this here. That is, the determinant was this term times this term minus this term times this term. So here we are, that's this term times this term, and minus this term times this term is that there. We've got to watch our minus signs carefully here because we've got an I squared in the middle. But what that turns into is 1.5 minus lambda all squared minus a quarter. That's what we get from multiplying these two minus 0.5s with the additional I squared in here. Has to be 0. Or equivalently, we can multiply this out, and what we've got is a quadratic. Lambda squared minus 3 lambda plus 2 has to equal 0. Well, of course, we can solve that quadratic equation. That's straightforward enough. And if we do so, we'll get these roots here. So lambda 1 equals 1, or another root is lambda 2, we'll call it, equals 2. These are the eigenvalues. These are the values of that parameter lambda for which there will be solutions of our original eigenvalue equation. So we substitute these values back into our original eigenvalue equation and deduce the corresponding eigenvectors. Let's just see that working. So our original eigenvalue equation was this one, and we've now figured out what values of lambda will allow this equation to have a solution. So for a given eigenvalue that we choose here, we're trying to find out then what will be the eigenvector, that is, what will be the values of d1 and d2 here. Rewriting this equation here, we can simply take this over to the left-hand side. So 1.5 minus lambda, that's having taken that over on the diagonal here, minus 0.5i, 0.5i as before, and then again we've got minus lambda d2 to put on the diagonal here. So we've taken all this stuff on the right and pushed it into the matrix on the left. We're left with the 0 vector on the right. We can evaluate this now for a specific eigenvalue. So let's take, say, the first eigenvalue, lambda 1 equals 1, that we just figured out. So putting lambda 1 equal to 1 into this matrix here gives us this matrix equation. And now, conveniently, we can actually go back to writing out the matrix equation as a couple of linear equations. So this matrix equation here is the same thing as these two linear equations here. And from either one of these equations, it doesn't matter which one, this was the first of them, this is the second of them, we can now deduce the eigenvector, because either one of these equations simply gives us that d2 is equal to I d1. So we could take this equation here, we would have 0.5 d1 is equal to 0.5 I d2 over here. In other words, d1 is equal to I d2. And you'd get the same answer if you took the second equation. Now, with eigenvectors, we are free to choose any one of the elements here. It doesn't really matter what we choose for one of them. All we have is a relation between the two of them. So let's choose, say, d1 is equal to 1, which gives us the eigenvector v1 here, v1 equal to 1, I. And similarly, if we went through the same process using lambda 2 equal to 2, we would get the other eigenvector, which would be 1 minus I. For larger matrices with eigensolutions, that is, so for some n by n matrices here, we would have correspondingly higher order polynomial secular equations, and those might get hard to solve, but they in principle might have solutions. And they would then give us n eigenvalues and eigenvectors, if those eigenvalues and eigenvectors exist, if the solutions exist. So a 3 by 3 matrix can have 3 eigenvalues and 3 corresponding eigenvectors. Note, incidentally, as I said before, when we had the freedom to fix one of our elements in our 2 by 2 matrix eigensolution, eigenvectors can always be multiplied by any constant and still be eigenvectors. It doesn't matter.